What does the E and B fields actually look like inside of a conductor when you have an electromagnetic wave entering it? Well, the answer is not simple, but this is section 8.32, Monochromatic plane waves in a conductor of Griffith's Introduction to Electrodynamics, second edition. And here we're going to examine what the E and B fields actually look like and how they relate to each other, and we'll get a little pretty picture, and then we're going to examine the energy and how it works inside of there. So the E fields and B fields have a formula that looks like this. So the E field is complex, x comma t. It's equal to some complex E naught. That's a vector because it has the polarization in there, times e to the I kappa, but kappa is complex, x minus omega t. And the B field is much the same. That's complex. That has to equal B naught. That's a vector. E to the I kappa complex, x minus omega t. And grab a different pen here. I'm not liking this one too much. I don't have much of a choice, do I? The third rule of Maxwell's equations relates the E and B fields by this. It says the curl of the E field must equal negative the time derivative of the B field. If we take the curl of the E field, well, first let's assume that this E vector, this is going to be some complex number j, and this one will likely be independent. This one, well, the curl of that. Well, what's the curl of this? The only variation we have in the positionals is according to x, and so it's going to be d by dx of this, of the of the y component of the field here. That's going to point in the k direction, and that has to equal minus d by dt the B field, which is just simply plus I omega, the B vector, B naught complex e to the I kappa x minus omega t, and as you can tell, it's going to have to go in the k direction. So now we know that the B field is aligned in the k direction. The positional derivative, we bring down the complex kappa, so we get I kappa E naught complex e to the I kappa complex x, this is complex, minus omega t equals this I omega B naught complex e to the I kappa complex x minus omega t. This is all in the k direction. Okay, so we get the result that B naught is equal to kappa complex over omega of E naught complex. Now, this doesn't tell you much right away, but if we do the sidebar here where we say, let's suppose that our kappa, which we already know is this kappa plus I kappa minus, let's rewrite it this way. It's also equal to the magnitude of kappa times e to the I phi. Phi, I guess is the right way to pronounce that, but some people call it phi. Where this, this is just simply the square root of kappa plus kappa minus, both of them squared, which simplifies out to be the mildly dramatic and complex square root of 1 plus sigma over epsilon omega squared, excuse me, and the phi, of course, well, tangent of the phi is just the negative divided by the positive components of that. So this can be rewritten like this. So we have B, which is going to be some real number, times e to the I, the phase shift of the B, is going to be the magnitude, times e to the I phi, divided by omega, e naught, e to the I d e. Okay? And so this leaves us the conclusion that B naught is equal to kappa over omega E naught, and the phase constant of the B field is equal to the phase constant of the E field plus phi. Okay, those are some rather important conclusions there. I'll highlight those for a minute. So the B field is trailing. It's not in sync with the E field like it was in non-conducting media. It's actually trailing it. To get a better picture of what that looks like, let's take the reals of these and let's draw a graph here. let's get a nice big piece of paper here. So here we have that. And we're going to have our electric field and magnetic field. They are going to have, let me write this out in its full glory here. So E vector is equal to E naught. Then we have the imaginary. This is minus kappa minus x, e to the I kappa plus x minus omega t. This is the wavy part, this is the attenuation part, and the B vector is going to be magnitude of the complex divided by omega times E naught, and then we're going to have the attenuation part just like the electric field, and then e to the I kappa plus x minus omega t plus phi. Okay? It has this phase constant introduced that that puts it out of phase with the E field. Okay? So both of them have this attenuation, this logarithmic attenuation. They both go like that. And I'm going to draw the, let's see, J, let's do this. This is X, Y, this is the direction of the E field, so this is X, Y, Z. This has to be the direction of the B field. So the B field is going to do the same kind of attenuation. It's going to start out maximum and then it's going to attenuate the same way, except for it's in a different plane. So if the E field is going to basically do a wavy wave, and I changed the frequency that it's not supposed to change. Shoot me. It's supposed to have the same time period. Okay, it's not supposed to, these intervals are supposed to be the same. And the B field is going to trail slightly depending on the material. So it's going to start up here and then come down here and then go over there and then come back and then go over there and come back and so on. It's going to be smaller and smaller. It's really hard to imagine exactly what this looks like. The book has a good drawing, but imagine that you had these two fields lined up and then you have to push the B field back a little bit because of the phase shift. And that's basically what it looks like. Hope that was terribly informative. The next thing to think about is the energy in the field. So U is going to be equal to 1/2 of epsilon times the E squared plus 1 over mu times the B squared. Okay? And if we write this out, we're going to have 1/2. And both of these fields share some stuff that's in common. So let's bring out the common stuff. So we're going to have E naught squared, and then all of this stuff and all of that. E is squared, so it's kappa minus x. And then, well, we're doing reals, I guess, so let's stick to what the book is doing. And this is all multiplied by epsilon times the thing that makes E special, which is the cosine squared of this garbage, kappa plus x minus omega t plus whatever phase constant that the electric field has, plus 1 over mu squared. No, the mu isn't squared. And then the B field has this constant that it multiplies by. So that's going to be kappa squared divided by omega squared. And there's going to be cosine squared of the same stuff plus some phase shift. Okay? It's based on the K, complex K that we calculated. If we average over an entire cycle, we're going to get this result. 1/4 epsilon E naught squared e to the minus 2k minus x times 1 plus the square root of 1 plus sigma over epsilon omega squared squared, and that's it. Okay. The second term, this term, is a lot greater. When we did the non-conducting media, we found that the E and the B fields contribute equal amounts, but here in the conducting media, we see that this term is much larger, that this is always going to be greater than 1 over here, depending on how the sigma over E relates. The good conductors, so where sigma over E gives you a value that's much greater than 0, or much greater than omega. So in those cases, we can simplify for good conductors. We get our U about equal to 1/4 sigma over omega epsilon naught squared e to the minus 2 kappa minus x. Okay. So basically, these two terms dominate. Omega basically becomes very small. Wait, that's not right. Sigma over epsilon. Sigma over, yes, this becomes very large, I think, and it crowds out the rest. But the important thing to remember is that we have this attenuation constant, attenuation term here that will make whatever energy transferred steadily reduce in size. The flux is given by the energy flux is by the Poynting vector. So S vector is equal to 1 over mu E vector cross B vector. Well, what's that E vector cross B vector? That's going to be, we're going to have that 1 over mu term. We're going to have the contribution due to the B field, so we're going to have kappa over omega. And we're going to have the 2 of the E naughts. We're going to have 2 of those minus kappa minus x, e to the kappa minus x's. And then we're going to have cosine of this bit, I'm going to call this A, times cosine of A plus phi. Okay? That's the S vector. If we want to average that over the average of that S vector, this is going to point in the I hat direction, by the way, for our fields that we chose. So taking the average of this, you basically want to take the integral from 0 to 2 pi of blah d theta, right? Or whatever. Yes, something. And then you can divide by 2 pi. And this bit has to go in there for A. Well, actually, let's say this is theta instead of A. I should have used theta because that's what the book used. So when you plug this in, it's a rather complicated integral, but the end result is that this bit is going to end up being 1/2 cosine of phi when you solve that integral and do the averaging. So the end result is that you get 1/2 1 over mu omega, actually k, e naught squared e to the minus 2k minus x. That's pointing in the I hat. That's the average S. Okay. Example 6. Checking the time. We have plenty of time. Example 6. I found this really hard to follow at first, but it's actually a lot simpler than I thought it was. So imagine we had a slab of tiny, tiny, tiny width dx, delta x, and the area A. Okay, and we're going to calculate the amount of energy lost inside of that slab. So we're traveling. This is x. Okay. So the power formula, E dot J d tau over some volume. Excuse me. What's E? Well, that's just the E field. What's J? That's just sigma E. What's the volume? That's A delta X. That's the volume there. Then the other, so the average, so what's our E field? This is our E field. We take the average power, and we're going to end up with 1/2 sigma E squared, E naught squared, E to the minus 2 kappa minus X times A delta X. Okay? We've already solved the average of that. I didn't solve it, I just read from the book basically, but you get the idea. what if we took the S vector on one side versus the S vector on the other side? Well, the S vector on one side, the S vector flowing on the inside times the area. That's going to give us 1/2 kappa plus mu omega. Oh, that's right. Oof, I forgot an important thing here. This is 1/2 cosine phi. Well, kappa cosine phi is just kappa plus. That's just the real part of that kappa. So it's 1/2 kappa plus. E naught squared, e to the minus 2 kappa minus x, and times the area. Okay? So that's the energy flowing into one side. The energy flowing out of the other side is basically the same, but you have x plus delta x. Okay? Now, if we wanted to calculate the difference between the two, we'd have to take the derivative and then multiply by the width there, assuming the width is very small. So the difference, the average power lost on the inside is the difference. And then take the derivative of this. Well, what's that? Minus 2 kappa minus times e to the minus 2 kappa minus x a delta x. Okay. So we have the 2's cancel. We have minus. Why do we have minus? Oh, we take the minus of the derivative, so this is going to be positive derivative. Okay. Minus the derivative, so the difference, yes. Remember the derivative d by dx of f is just the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. In this case, we're taking f of x minus this, so it's negative derivative. This is negative d by dx of the stuff on the inside. Okay, and then we have to multiply by the width, delta x. Okay, so we have a kappa plus, we have a kappa minus. Kappa plus times kappa minus gives us this little mess. So we have, over here we have this, over here we have this, and do the two relate. Is this equal to 1/2 sigma? Well, kappa plus times kappa minus, if you work it out, will give you 1/2 sigma mu omega. Well, that ends up being 1/2 sigma that. And so they end up being equal. So calculating either by the Joule heating law with the electric and the current, or calculating it using the Poynting vector will get you the same answer, which is kind of cool, with all the caveats attendant to that. So thanks for your time. Be sure to like and share this video with your friends, and let me know if you need help or additional clarity in the comments below. Thanks for your time. Bye-bye.